Hi and welcome to this Leaving Cert Higher Level Maths revision video. We're looking at Worksheet 3. So this is a COVID-19 edition because I've specifically looked at questions that might appear on the actual paper if they wanted to bring in COVID, which is quite obviously topical. So this is a combination of previous mocks and exam questions. Question 1, this is about a viral infection. It's an exponential functions question which includes a bit of calculus. It's 25 marks, and what I will say, it is a mock question. It is particularly challenging. However, some of the elements that they ask, it's really nice to see. The number of people infected by a viral infection in a town can be modelled by this function, where t is the time in days from when the infection first appears. How many people are infected initially? So when we talk about initially, we mean the start, which means when t equals 0. So this is a little substitution question, quite straightforward. So we're going to sub into our formula. Everywhere there is a t, we're going to put in 0. That simplifies down to having e's to the power of 0. Remember, no matter what the number is to the power of 0, that means 1. The power 0 really means when you've divided something by itself, that's where we get that power 0, so the answer is always 1. There's no way we can ever divide and get 0 unless we've already started with 0. So e to the power of 0 in both of those cases is 1. That simplifies down to 20,000 over 200, which gives us an initial, the number of people who are infected initially as 100. Part 2, find an expression for t in terms of n and hence deduce the range of values for n. Okay, so this is a manipulation of formula question, and the word deduce obviously has come up a few times, and I know sometimes students question that, and what it means is just figure out. Okay, so deduce, based off what you've done, deduce, figure out the range of values for n. Now, we're going to take what we had originally, so our original formula or original function, whatever way we want to think of it, and we're going to try and now rearrange this and isolate t. So first thing I'm going to do is I'm going to multiply both sides by the denominator. That will end up giving me n times 199 plus e to the power of 2t is equal to 20,000 e to the power of 2t. Multiplying that out, get a 199n plus n times e to the power of 2t equals 20,000 e to the power of 2t. Because we're trying to isolate t, we're trying to find an expression for t, we want to bring all t's to one side. I'm going to bring it all to the right hand side, so I'm going to take n e to the power of 2t from both sides. This is what it looks like. However, I like working with whatever I want on the left, so I'm going to flip this equation once I've done that. You can move things over to the left, but I would just be wary of there's a negative then on both sides, and I'm not a big fan of working with negatives if we can avoid it, because it's easy to lose the minus. So what I'd suggest there is if you do move I suppose the terms with t to the left rather than the right, then that you just maybe multiply both sides by -1 to get rid of the negative really in front of the 199n. That's the one that I think would be nicer as positive. So I'm just going to flip this now. I have a nice little equation. I have two terms with a t. How I suppose it's a trick, or it's a thing to remember. How do we bring the t from two terms into one single term? And the answer is highest common factor. So we pull out the e to the power of 2t and we're left with this. We can then divide both sides by 20,000 minus n. So I get e to the power of 2t on its own. And now I'm very, very close. I want to get t on its own, but now I have t, but it's in a power. So if we want to take it from the power, we need to use logs. So I'm going to use, you can use the circle method, you can take the natural log of both sides, you can use the formula in your log tables, but when we rearrange it, we'll end up with 2t equals log to base e of that fraction. Now, log to base e is just another way to say natural log. So if you went straight to natural log, that's perfect. So then to get t on its own, we're going to divide that whole thing by 2. Now that's not very nice. We rarely use that division sign. I would use it at the end of questions where I just want to put it into my calculator, but here this is not ideal. So instead I'm going to take this and write it as a fraction. So put it over 2, or nicer again, dividing by 2 is the same as multiplying by a half. So it would look like this. Now that's all just different ways to rearrange the same thing. This last part is really, I would say, the nicest way to present your work. The second last line, that complex fraction, it's fine, but it's not that easy to work with. So that idea of dividing by 2 is the same as multiplying by a half. So now I'm going to try and deduce a range of values for n. So time will have to be greater than or equal to 0 because it has to start. Time can't be negative. So that's where I'm going to start. I'm going to say, well, this fraction must be greater than or equal to 0. I can multiply both sides by 2 to get rid of that fraction, and I end up with the natural log of this is greater than or equal to 0. Now, there's a few different ways you can think of this, and I do think that inequalities with logs can be quite challenging, and I often recommend that maybe you work with the equation and then figure out an answer from there. But I suppose if we think about it, we have to have a positive answer in there in our fraction. So what we end up with is actually, if I take that fraction, it should be greater than or equal to 1. This might be challenging to understand, and this is quite a challenging piece. If you work with kind of taking e of both sides, which is kind of one method. So if we put e and put this to the power and e to the power of 0 there, e to log to base e, not that they cancel, but they kind of undo each other and leave us simply with a fraction, while e to the power of 0 gives me 1. I think that's the easiest way to kind of get our heads around why that's the case. The circle method, I suppose, is challenging because it's great to use when there's an equals, and the same for the conversion formula in our log tables, but it kind of doesn't give us the full idea with how that inequality should then be placed. If you want to think of it in a more logical way, if I look at the fraction itself, I have e, the log to base e of some number is greater than or equal to 0. And again, if this fraction here that I have drawn around in green, if that is any number less than 1, I'm going to end up with an answer that is negative. And I suppose you can try that out in your calculator. So you can do ln, natural log for short, and then do 1. So if we do the natural log of 1, it gives me 0. But if I go down a bit, so let's say the natural log is 0.5, I get a negative answer. If I do natural log of 1.5, I get my positive answer. So you can use a little bit of kind of logic there. I think once you've seen this once and you really focus in on it, it will help if you ever met something like that again. But I can understand why this step here, so from here to here, why that is a challenging step. So let's work through it then. If I know this fraction must be greater than or equal to 0, I can multiply both sides by the denominator because it will be positive. I don't have to worry about squaring or anything like that. I add n to both sides. That gives me 200, and n is greater than or equal to 20,000, and divide both sides by 200. So I get n is greater than or equal to 100. Now, did we need to do all this work? Well, actually, we had already figured that out. We knew initially that that was 100. So the word deduce often means kind of figure out, but not necessarily calculate. So we got the exact same answer by simply looking at part I and going, well, if when time is 0, there is 100 cases, it's exponential, so it's only going to grow. Therefore, the smallest number of infections would have to be 100. Okay, so we could get that very quickly from part I, and without all that funny logs and working through it. But do I have a cap? Is there a number that it can't exceed? So for this one, I'm going to go back and kind of understand, well, if I want this fraction, let me show you which fraction I'm looking at. So if I want this fraction greater than or equal to 1, I said that I'm multiplying both sides by the denominator, and that's okay because the denominator is positive. And that's important. So that denominator, it has to be greater than 0. It has to be. Because first of all, I can't divide if it's 0. It's not possible. Can't divide by 0. And secondly, if it's not, so if it is negative, I'm going to end up with a negative number, so it can't be bigger than 1. So here I have 20,000 minus n is greater than 0. Bringing that 20,000, so I'm taking 20,000 from both sides. I like to change the sign and flip the inequality, so my inequality flips to a less than sign here, so n is less than 20,000, and that gives us a final answer of n must be between 100 and 20,000. It can be 100, so it's less than or equal to sign there, but it cannot be 20,000. Part 3. By finding dt dn, show that dn dt, the rate at which the infection is increasing, can be written as this fraction here. Okay, so basically what I'd like you to see straight away, and maybe you did, is that dt dn and dn dt, they're reciprocal. So when you flip them, they are the same. So for example, dt dn, if we flip them, is dn dt. Okay, that's important. So when I work out dt dn, I can flip it to get dn dt. The formula for differentiation of log specifically, because remember we have a log equation here, it's in the formulas on page 25. It's here. It's when I have the natural log of x, it gives me 1 over x. So here is what I have. This is t, and I'm going to work out dt dn. So I'm going to differentiate t with respect to n. That means n is the thing that I do my rule to. So I have the natural log of this. So the half is a coefficient that doesn't get involved. But my formula in my log tables is for the natural log of x. I do not have the natural log of in just n in this case. I have something more complex. What I actually have here is going to be the chain rule, because I have a function within the function. So that's my inner function there circled in red. So I'm going to differentiate using my natural log rule, but I then need to multiply by the derivative of the inner function, which means I need to differentiate that piece in red. So what it's going to end up like is dt dn is equal to a half. Remember, the coefficients, they just sit there. They don't get involved. They will just be there. It's like having a 3x. The 3 just stays there. 3x squared. The 3 just stays there. So half stays there. I have differentiated my natural log of the fraction to 1 over the fraction. But since that was a fraction and not just simply n, because in this case we're talking with respect to n, I need to multiply by the derivative of the inner function, which is this red piece here. So I'm going to take this little red piece, I'm going to call it y, and I'm going to differentiate it. Now why I've called it y is because this is not even nice, easy differentiation, because this needs the quotient rule, because it's a fraction. So there's lots of layers here, lots and lots of layers. I will talk you through another method, but for now, let's look at this. So I have u, which is the top line, v, which is the bottom line, so my numerator and my denominator. I differentiate both with respect to n. So du dn is 199, dv dn is minus 1. When I work that out using my quotient rule formula, this is what I get. Okay, so that is v. It's meant to be du dx, but we have du dn minus u dv dn all over v squared. I'm going to tidy that up, multiply it out. I'll have 20,000 by 199. Then that's 3,980,000 minus n by 199. That's minus 199n, and then minus 199 by minus 1. Sorry, minus 199n by minus 1 gives me a positive 199n, and that they kind of cancel each other out. I have an add 199n, take away 199n. It leaves me with 0. So this is what I'm left with. So that gets put in as an extra multiplying at the end of my dt dn. Okay, so I multiply by the derivative of the inner function. Usually that's nice. Usually that's something nearly you could do in your head. But here, because we needed the quotient rule, we needed to work aside. So my final answer for dt dn is a half times 1 over 199n over 20,000 minus n times 3,980,000 over 20,000 minus n squared. I haven't multiplied out that denominator. I've left it, and I'll multiply it out if needed in a minute. So we have ddtn as this, which is quite complicated, and we want to simplify it. Specifically, we want to work with this complex fraction. Complex fraction is a fraction within a fraction. What I find it easier to do is to write this as actually division. So we have 1 divided by that fraction, the denominator. Instead of dividing by a fraction, it's much easier to multiply by its reciprocal. So we multiply and flip the fraction, and that simplifies to simply 20,000 minus n over 199n. Now we can start simplifying this fraction with common factors above and below. So we have 2 and 199. When we multiply those together, we get 398. Then we can divide that into the top line, leaving us with 10,000. The fraction, the bottom of the second fraction is a bracket squared. One of those can be divided into the 20,000 minus n, so we can cancel them out. And if we simplify this, so now be careful, there's still an n in the denominator of the first fraction, there's a 10,000 at the top of the second fraction, and then 20,000 minus n at the bottom of the second. So this is what it simplifies to. Now, we weren't asked for a dt dn, we were asked to find this to in turn help us to find dn dt. So that is its reciprocal, so we're going to flip it. So when we flip the fraction, we get exactly what they've asked us to do, so QED. Part 4, hence find the number of people infected when the infection rate is spreading most rapidly. This is a very, very tricky question. What they're asking us to do is to find where the rate itself is at a maximum. So we need to take the rate, differentiate it, and let it equal to 0. So here's our rate, dn dt. In order to differentiate it, I'm going to simplify it by expanding the top line and splitting it into 2 fractions. This simplifies to 2n minus n squared over 10,000, which is a negative quadratic where we will be able to get that maximum point. There will only be one turning point. It will be a maximum, so we won't need to check. To differentiate this, I'm going to write it as the second derivative because that's what it is. And I bring down the power, take 1 away from the power. 2n differentiates to 2. Minus n squared over 10,000 is minus 2 times n over 10,000. And that simplifies to 2 minus n over 5,000. To find the maximum, or a minimum turning point, in this question it just happens to be the maximum, we're going to let that equal 0 and we're going to solve for n. So I bring over I take a 2 from both sides. I'm then going to change my sign so it becomes n over 5,000 equals 2. I'm going to multiply both sides by that 5,000 and that will give me n equals 10,000. This is not the maximum number of people that are infected. Instead, this is the number of people that are infected when the infection is at a maximum rate. So it's where it's spreading most rapidly. Question 2. Here we're looking at a question about flu symptoms, and maths-wise we're looking at exponential functions including a graph. This was 45 marks. A group of medical students in a certain university are studying a number of students on campus who begin to show flu-like symptoms during the month of January. The population of students displaying symptoms can be modelled using this function. P of t, be careful, that means P of t, so it's a function in terms of t. It does not mean multiplication, be so careful there. So P of t is equal to a e to the power of bt, where a and b are elements of the real numbers and t is the time in weeks since the beginning of the study. On the first day of their study, 4 students were displaying flu symptoms. After 7 weeks, 23 students were showing flu symptoms. Use this information to show that A is 4 and B is 0.25, correct to 2 decimal places. We're seeing more and more questions about showing rather than calculate or finding, because then if something goes wrong, you do still have the right answer to move forward. So it's important that for any subsequent parts, any next parts, that you use the correct answers rather than your own, because it'll be easier to correct. So let's start with the initial point. These questions always give you an initial, so we can easily work through it. So when t is 0, P of 0 is 4. So that means the population of students displaying symptoms is 4. Working with that, P of 0, it's AEB to the power of 0 equals 4. That is B times 0, which is 0. So we get AE to the power of 0 is 4. E to the power of 0, that is an exponential. We are looking at where the power is 0. Anything to the power of 0 is 1. So this gives us A is 4. exactly what they've asked us to show. The second piece of information they gave us was when T is 7, the population of the students displaying symptoms was 23. So P of 7 equals 23. So P of 7, and I'm going to sub in now that I know A is 4. That leaves me with simply one unknown to find. So 4 times e to the power of b times 7 equals 23. So we're subbing in, instead of t, we're subbing in 7. When we simplify this, we get 4e to the power of 7b equals 23. I'm going to have to work with logs, but before I do, I need to know that I need to make sure I have e on its own. So e to a power, there can be no coefficient. So I'm going to divide both sides by 4, and then either using your circle method, the conversion in your log tables, or if you want to take both sides to the natural log, we're going to end up with 7b equals the natural log of 23 over 4. That's log to base e. To finish it, I'm going to divide both sides by 7. I like to show this as a division. I don't usually put that natural log into my calculator till the very end because it's quite a long decimal. So we can do that into the calculator and we end up with 0.249885693. We want it correct to 2 decimal places, so that gives us 0.25 as they told us it should. Part B. Find the number of students who displayed flu symptoms after 15 weeks, correct to the nearest whole number. So like I said, if part A went wrong for you, you should still have used the A and B value that they gave us. So now we know that the actual function is not AE to the power of BT, but rather 4E to the power of 0.25T. We're being asked about the number of students after 15 weeks. So we're talking P of 15. So everywhere there's a T, we're subbing in 15. We work that through and we get 170.084328. They did say the nearest whole number, but we should have been able to do that anyway, because remember that this is the number of students. Number of people should always be whole numbers. This is 170 students. Part C. How many weeks did it take for 50 students to display flu symptoms? Correct to the nearest whole number. So again, we're going to work, and they've told us this time T. So we know that when we sub in some number for T, our answer will be 50. So in this case, we're working backwards to find T. I have this set up, but I need to make sure before I do any changing to logs that I divide both sides by 4. How I know that I need to use logs here, there's a very simple technique, and what I would say is if you can put the power into your calculator, you're fine. If you can't, then you need to change to logs. So because the unknown is in the power, we're going to need to use logs to take it out of the power. So can I put it into the calculator as is? No, so I need to change it. And that works for changing logs back to indices as well. So now, whichever way you want to do it, circle method or your formula in your log tables or taking the natural log of both sides, we end up with 0.25t is equal to the natural log of 25 over 2. I want t, so I'm going to divide both sides by 0.25. I wait till the very end to put that into the calculator, and I end up with 10.1029148. So the final answer here, I would be saying T equals 11 weeks. I feel like if we were working in a situation like this, and we went down to 10 weeks, that there wouldn't be 50 students, there would be less than 50 students. So is that technically true? Oftentimes in a question like this, where it's ambiguous as to, which really is the correct way to round, they would, in an exam situation, so in the actual Leaving Cert, award marks for both. So I would be saying, yeah, okay, they'll probably give you the marks for 10 because it does round down to 10. But for me, how many weeks did it take for 50 students? Technically, for me, 10 wouldn't be correct, because if we put in 10 weeks, we would just have under 50 students. So I suppose a little bit of ambiguity there with our final answer, but I will be going with T equals 11. Part D, draw a graph to show the number of students displaying flu-like symptoms for the first 5 weeks of the study. So what I'm going to do is I'm going to take my original function here and I'm going to work over the first 5 weeks. So we can sub in t equals 0 and get 4, or you can use the fact that we've already worked out that initial answer was 4. So let me plot the points as we go. So that is 0, 4. That's our starting point. Then we try when t is 1. That gives us 5.31. So that's about 5.5. So about 5.3 about there. Our next one when t is 2. That gives us 6.59. So t2 6.59. It's about 6.6. So about there. Our next one then when t is 3, we end up with 8.46. So about 8.5ish, so about there. Oh, my 2 point disappeared. So 2 and 6.6, about there. And when t is 4, 10.83. So 10, so it's probably up near the 11. And then finally, for t equals 5, we get 13.961, which is practically up there on 14. So right there, we connect that. Here's slightly nicer version that someone else has drawn on computer. So we get that nice curve, but you'd be just connecting your dots. Question 3, testing for disease. So this is a probability with some hypothesis testing, and it was 45 marks. So blood tests are sometimes used to indicate if a person has a particular disease. Sometimes such blood tests give an incorrect result, either indicating that the person has the disease when they don't, which is called a false positive, or indicating that they do not have the disease when they do, so called a false negative. It is estimated that, so let's get the highlight right, 0.3% of a large population has the particular disease. Okay, so that's given to us here. A test developed to detect the disease gives a false positive 4% of the time. So false positive means they don't have the disease, but they do test positive. So that will go in here. So there's our 0.4. And a false negative in 1% of tests. So false negative means they have the disease, but show negative. And that's that number there. Person is picked at random and is tested for the disease. Write the probability associated with each branch of the tree in the blank boxes provided. So when we have a tree diagram, each of the branches, or so for example, if we were talking about here and here, so these branches should add to 1. So having one side of each of the branches filled in means we can easily calculate the others. So if I have 0.003, the other side is 0.997. At the top, 0.01, the other side is 0.99. And finally, if we have 0.04 already filled in, the next number is 0.96. When we look at the end boxes, so where it says, so let's look here. What we're trying to do is to find that the probability that a person has the disease and tests positive. So when we have the word and, we mean multiply. So we're going to multiply along the length of our tree. So we here to here brings us to this box here. So we're going to multiply 0.003 by 0.99 and we get 0.00297. We continue that trend and we end up with our final answers here. A quick check to make sure everything looks okay is to add all those answers, because that is an exhaustive event because it's a random person is picked. So yes, we're picking a random person, probability of that is 1. So the total of all of those boxes should give us 1, which they do, which indicates probably is correct. So now we have our little table, or we have our little tree up here at the top to help us. But part 2 says hence, so using this tree or otherwise, calculate the probability that a person selected at random from the population tests positive for the disease. So here are the 2 places where you can test positive. So you can have the disease and test positive, or you cannot have the disease and test positive. So they're the two options. Or means add. So what we're going to do is add these 2 answers together, and that gives us a total of 0.04285, which is the probability that somebody tests positive. I like to work in percentages. I think it's easier to understand. So I will always change my answer back to a percentage. So in this case, 4.285%. Also think about how the question was asked. The question did give us everything in percentage, even though we then went back to work in decimals. Part 3 then says a person tests positive for the disease. What is the probability that the person actually has the disease? Give your answer correct to 3 significant figures. Okay, so you can work this a few different ways, but I'm going to work here with conditional probability. That is the probability of A given B is the probability of A intersection B, or A and B, over the probability of B. So how I'm going to structure this is it's the probability that a person has the disease given they've tested positive. The probability of A intersection B is the probability that they have the disease and is positive. So that's our 0.00297 over a total of 0.04285, which is the total probability of them being positive that we worked out in part 2. You can also work this in a more logical way and say, well, I know the probability that they test positive, and then I suppose what's the probability that they have the disease out of that, and then it will be just this answer here. So I'm going to get a nicer color to work with. So we'd have these are the people who have the disease and test positive over the total amount of people, or the total probability of testing positive, again, which we worked out in part 2. You'd end up with the exact same fraction. It's just thinking about it in a different way. When we simplified, we got 0.0693 or 6.93% if you like me, to work in percentage. Part 4. I think this is probably just the most interesting question that has ever been asked. I absolutely love it. I think it really puts into context what we're doing. I think as an exam question, it's very, very difficult. It's very challenging to be thinking like this in an exam, but I do think it's something that you should be looking at outside of the exam situation. So as you're doing, I suppose, any kind of work on probability, or like now where we're looking at, viral infections and diseases and things like that. So the health authority is considered using this test on the general public with a view of treatment for the disease. So basically what they're saying is they're going to test people, and if they test positive, they're going to treat them. So based on the results, do you think the above test will be an effective way to do this? Give a reason for your answer. So at first glance, you might be like, yeah, it's good. It is a very low point. So I think it's like 1% that get it wrong. It's not so bad. But if we actually think about what we've just looked at, the probability that you have the disease given you've tested positive is 6.93%. So out of the people who test positive, actually only 6.93% of them have the disease. So this means that when a person tests positive for the disease, there's actually only a 6.93% chance they have the disease. You can think of that in terms of people. So there's a 6.93% of people have the disease when they've tested positive, the rest don't. I suppose a better or another way to look at this is, well, 93% of people who test positive actually don't have the disease. That's amazing. Okay, that's huge. So if we think of this, out of every 100 people who test positive and you treat, only 7 of them really need a treatment. That is definitely not an effective way to decide who should get treatment. So no. So part B of this, now this has come from the papers and it's an older question. What I mean by that is pre-2015. So if you're looking at the solution to this was before the inferential statistics questions were introduced properly. This means that the solution that was correct at the time is not the way we would work. So in case you're wondering why mine is looking very different or I've used different formula, that's the reason. I would disregard any of the questions before 2015, or instead maybe look at them through the lens of what we work with now. So a generic drug used to treat a particular condition has a success rate of 51%. A company develops 2 new drugs, A and B, to treat the condition. They carried out clinical trials on 2 groups of 500 patients suffering from the condition. The results showed that drug A was successful in the case of 296 patients. The company claims that drug A is more successful in treating the condition than the generic drug. Okay, a lot going on there. Let's pull out some information. We have a success rate of 51%. That is a proportion, that is P. So we're talking here about proportion. There's no mention of mean, there's no mention of standard deviation. We're dealing with proportion. We then have a sample, and in that sample we have 500 patients. 296 of them are successful. Okay, so that's going to be what we're going to use to get the proportion of the sample. P hat. We then have what is the claim. So the company claims that drug A is more successful in treating the condition than the generic drug. Use hypothesis tests at a 5% level of significance to decide whether there is sufficient evidence to justify the company's claim. State your null hypothesis, and state your conclusion clearly. Okay, so our null hypothesis, we're taking our P, so that is P equals 51%. Our alternative hypothesis, then P does not equal 51%. What that means in terms of like words is the success rate of drug A is 51%, or the success rate of drug A is not 51%. So what we really want to focus on is this one here, which is our claim, but basically they were a bit more specific and said that it is more successful, so that it is 51%. So really that the success rate of drug A is the same, or it is more than, less than. Okay, so this is very simple terms. Let's look at the confidence interval for the population proportion. Here's our formula. We use n as 500. P hat, so the proportion of the sample, can be calculated using our 296 and 500. That works out as 0.592, so that's 59.2%. But we do want to work in decimal here. You want to leave it in decimal and not percentage. Subbing into our formula, it looks like this, and tidying up, we end up with 0.5489 is less than or equal to P is less than or equal to 0.635, which gives us 59.89% is less than or equal to P is less than or equal to 63.5%. Okay, so looking at that as an interval, what does that tell us? Okay, so let's look at this with regards to our 51%. So 51% does not sit in the above interval, so the result is significant, so there's evidence to reject the null hypothesis. Now, that helps us so far. It means it's not 51%, but remember the claim was a little bit more specific. So based on the above, we conclude with 5% level of significance that the success rate of drug A is not 51%, but also based on P equals 51% sitting below the above interval, we can conclude that the company's claim that drug A is more successful in treating the condition than the generic drug, it seems to be correct.